Hello, and welcome to my new show that I have decided to make, and I am going to call it Math Gardens. So welcome to the Math Gardens. Math Gardens are wherever you want them to be. The purpose of this video, and the purpose of this entire series of videos, is multifaceted. The main purpose of these videos is fun. I just want to have fun. I consider this fun. So I'm going to have fun with this. And that's the main purpose of these videos. Another goal of these videos is that I am attempting to reteach myself math from the beginning. I want to combine all of the fractured pieces of math that I learned in school into one cohesive whole. Everyone learns math in the form of classes that you take over many years at many different schools and institutions. They overlap. This is a prerequisite for that, and yada yada yada. And I think that is a result of the way math has been developed. It's been developed over many thousands of years by many different people who have contributed their contributions. I believe, however, that math is better understood as one cohesive whole. So I would like to teach math that way, where one subject from start to finish. First, let's discuss thought. What are thoughts? Thoughts are an abstract reality that exists in your physical reality. This abstract reality is under your direct control and limited only by your ability to control it. When you use this abstract reality to create order in your physical reality or make predictions as to what comes next in the ever-changing nature of your physical reality, then you are engaging in logical thought. Mathematics is a subset of logical thought. Your first mathematical thought is of nothing. Yes, nothing. I want you to imagine nothing. Absolutely nothing. Now remark on the fact that that nothing that you hold in your mind is the only nothing you will ever experience. Nowhere in this universe is there ever truly nothing other than in your thoughts when you think about nothing. If a basket is empty, it still contains something. There are air molecules, light, gravity, fields of force, like the Higgs field and the electromagnetic field. All are contained within that basket. Even in the deepest, darkest voids of our outer space, there is never nothing. Nothing only exists in your mind. Now imagine a unit. What is a unit? Well, a unit is not nothing. A unit is something. What is it exactly? A unit is exactly the same as another unit. That is what a unit is. A unit is the same as another unit. Only in mathematical thought are two things ever truly the same. If you have two apples of the same kind, they will be very different under a microscope. Even two molecules of hydrogen of the same isotope and ion are never exactly the same. The electrons are absorbing and giving off different photons. Within the proton, the trio of quarks are constantly in flux and never the same as another trio of quarks within another proton. No two things are ever the same, except for in your thought when you think about units. So we can have nothing. We can have units. We can have this many 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 units. Can we have a better way of organizing all of these different quantities of units? Let's label the quantities with a symbol and give each symbol a name. We will call nothing 0 and give it this symbol. We will call this many 1 and give it this symbol. We will call this many 2 and give it this symbol. This many will be 3 and have this symbol. This many will be 4 and have this symbol. This will be 5 and have this symbol. This will be 6 and have this symbol. This will be 7 and have this symbol. This will be 8 and have this symbol. This will be 9 and have this symbol. That is enough symbols. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now we will introduce the idea of a digit. Digits are a combination of symbols. The first symbol is 0. 0 represents nothing. The thing about nothing is that no matter how much of it you still have nothing. So a 0 is nothing, but 2 zeros is also nothing. These 2 zeros are the 2 digits of a 2-digit number, the number 0. No matter how many digits of zeros you have, you will always still only have nothing. So then, as we count units, we are going through the symbols in the first digit of these numbers. Since the zeros are just nothing, there is no reason to write them, but technically they are still there. So when we reach the last symbol, which is 9, we go back to the first symbol, which is 0, and move the next digit to the next symbol, creating 10, which is a combination of the symbols 1 and 0 in the first and second digit, respectively. This is because we have 10 symbols. If we had more or less symbols, then counting would be different. For example, what if we only had 3 symbols, 0, 1, and 2? Then counting would look like this. We start with 0 and its infinite digits. We only write the first digit and simply remember that the rest are there. Then this many is 1. This is 2, which is the last symbol. So we take the first digit back to the first symbol and move the next digit to the next symbol. Therefore, this is 10, 11, and 12. And then we go back to 0 in both the first and second digit and move the third digit to the next symbol, creating 100. And then 101, 102, 110, 111. Counting from 1 to 10 seems very universal to us humans with 10 fingers, but it is just a system that has been adopted far and wide. It is not some universal reality in and of itself. It is just a thought. Now, instead of labeling this many with a symbol and this many with a symbol and so on, what if we label the units themselves with these symbols? Then this is the 1, this is the 2, this is the 3, and so on. Now we can get rid of the units and just use the symbols. This is what we call a number line. The thing about lines is that they are like downward spirals. Downward spirals are only downward spirals until you turn around, and then they are upward spirals. So if our number line can go in this direction, then can it go in the other direction? Yes, we can if we label the symbols with an in the other direction symbol. We will use a little dash and call it negative. Therefore, the numbers with no negative symbol will be called positive. So this is 1 and this is negative 1. How does that look with our units? Well, we can have a unit and a backwards unit. Works for me. So we have units and backwards units. Can we have upside down units? Sure. Can we have upside down and backwards units? Absolutely. How does that relate to our number line? What is an upside down number line? We must have a symbol for upside down units. Let's use the letter I and call these numbers imaginary. Now, I know what you might be thinking. How can we have imaginary numbers? Well, remember, all of this is imaginary. Mathematics only exists in your imagination. Then for units that are both upside down and backwards, we will use both the negative symbol and the I. What does that look like for the number line? If these are positive numbers and these are negative numbers, then the positive imaginary numbers look like this, and the negative imaginary numbers look like this. Are there shortcuts in counting? There are, and the first is called addition, or plus, and we'll use the addition symbol. Addition is only a shortcut if you memorize your addition tables. Addition is a simple way of combining two sets of units by counting them both. 2 plus 2 looks like this set of units added with this set of units to produce this set of units. Therefore, 2 plus 2 is 4. If we add I units with other I units, the result is the same. This many I units added with this many I units is 2I plus 2I, which is 4I. Now let's say that we added positive units with negative units. Whenever a positive unit is added with a negative unit, they cancel each other out, like matter and antimatter. So 2 plus negative 2 is first these two units, then we add them with these two backwards units, and then this unit and this backwards unit cancel each other out, and this unit and this backwards unit cancel each other out. Then we are left with no units, which is 0. Therefore, 2 plus a negative 2 is 0. This is true for upside down units adding with backwards upside down units. They too cancel each other out. So this many upside down units added with this many upside down backwards units, it's 2i plus negative 2i, which is 0. We cannot add units or backwards units with upside down units or upside down backwards units. So this many units added with this many upside down units is 2 plus 2i, which is as simple as that can be written, 2 plus 2i. Subtraction or minusing is another shortcut in counting and uses the same symbol as negative numbers, except in this context, this symbol is called the subtraction symbol. When one set of units has another set of units subtracted from it, units cancel each other out the same way that units and backwards units cancel each other out in addition. So 2 units having 2 units subtracted from it is this many units having this many units subtracted from it, which means these 2 units cancel each other out and these 2 units cancel each other out, and we are left with nothing, which is 0. Therefore, 2 minus 2 is 0. If we subtract units from nothing, then those units become negative units. If we have this many units having this many units subtracted from it, then these 2 units cancel out with these 2 units, leaving nothing, which is 0. Then the last unit is subtracted from 0, transforming that unit into a backwards unit. Therefore, 2 minus 3 is negative 1. If we subtract negative units, then those negative units become positive units. So this many units having this many negative units subtracted from it transforms those negative units into positive units, and we are left with this many units. Therefore, 2 minus negative 2 is 4. As you can see, since we use the same symbol for both subtraction and denoting negative numbers, we have 2 of these symbols right next to each other. To avoid confusion, we always place open parentheses in between these 2 symbols. All open parentheses need a closed parentheses. Subtraction with I units and backward I units is the same as it is with units and backwards units. Like with addition, units and backwards units cannot be subtracted from upside down units and upside down backwards units. Multiplication is another shortcut if you learn your multiplication tables. Multiplication or timesing is denoted by these 2 symbols, which are interchangeable. If you have this many units, then we can think of this as a set of this many units. Then we can count a certain number of these sets. Then count the units in the result. So if we have this many units in a set and this many of those sets, then the result is this many units. Therefore, 2 times 3 is 6. Conversely, if we have this many units and this many sets of those units, then we have the same result. Therefore, 3 times 2 is also 6. When multiplying backwards units, we can have this many units in this many backwards sets. When units are in backwards sets, they become backwards units. Therefore, 2 times negative 3 is negative 6. When backwards units are in a regular set, they remain backwards units. Therefore, this many backwards units in this many sets produces this many backwards units. That means negative 2 times 3 is negative 6. If backwards units are in backwards sets, then they become regular units. Therefore, negative 2 times negative 3 is positive 6. Upside down units can be grouped into sets that can be thought of as units. Upside down units in sets as well as units in upside down sets produce upside down units. So this many upside down units in this many sets is 2i times 2, which is 4i. If we have upside down sets of units, then we have this many units in this many upside down sets, which is 2 times 2i, which is 4i. If we have upside down sets of upside down units, then we can have this many upside down units in this many upside down sets, which is 2i times 2i, which is 4i squared. I forgot to tell you that I squared, or an upside down set of an upside down unit, is negative 1, or a backwards unit. Now, why is an upside down set of an upside down unit a backwards unit? In other words, why is I squared negative 1? To put it simply, an upside down set of an upside down unit is a backwards unit, or I squared is negative 1, because of a combination of me being in charge and I saying so. You are on a need-to-know basis, and that is all you need to know. Now, we have already introduced the idea of sets of units, and thinking of sets of units themselves as units in multiplication, thinking of a set of units as a unit is what is known as a ratio. There are many types of ratios. The first is division, or dividing, and is denoted by this symbol or this symbol. If we have 6 units, then how many units are in 2 sets that are themselves units and produce the end result of 6 units? Well, since we already know that what a unit is the same as another unit, then whatever set we come up with has to be the same as any other set thought of as a unit with that set. So how many units are in one set that is one of 2 sets that are thought of as units that produce 6 units? That many, otherwise known as 3. So 6 divided by 2 is 3. If we want to know how many units are in 2 backward sets of units that can be thought of as units in 6 units, since we know that backward sets transform units into backwards units and backwards units into units, then we know that backward sets of units must contain backwards units in order to produce regular units. So this many units broken down into this many backward sets of units that can be thought of as units must contain this many backwards units in each set. Therefore, 6 divided by -2 is -3. If you have this many upside down units, then how many upside down units will be in each set of upside down units that can be thought of as units that will produce this many upside down units? This many units would be in this many sets that can be thought of as units that will produce this many upside down units. Therefore, 6i divided by 2 is 3i. If you have this many upside down units, then how many units will be in this many upside down sets that can be thought of as units that will produce this many upside down units? This many units would be in this many upside down sets that can be thought of as sets that would produce this many upside down units. Therefore, 6i divided by 2i is 3. Fractions are another example of ratios. What if we have this many units? Then how many units will be in this many sets of units that can be thought of as units that will produce this many units? Well, it's cutting a unit in half. We don't know about cutting units in half yet, so we'll just say that the simplest way to understand this is that this is the ratio between this many units and that many sets of units that can be thought of as units, and for now, that is as simple as we can say it. In other words, 5 divided by 2 is just 5 divided by 2. We can say that as 5 over 2 instead of 5 divided by 2. We can say that as 5 halves instead of 5 over 2. That all means the same thing. That all means the ratio between this many units and this many sets of units that can be thought of as a unit that produces this many units. In other words, the ratio between 5 and 2. The same rules apply to these ratios or fractions as with the rest of division with regards to units or sets being backwards, upside down, or backwards and upside down. 2 ratios can be added, subtracted, multiplied, or divided. Addition and subtraction requires the number in each set to be the same. If there are this many units in this many sets that can be thought of as units that produce this many units, and then you add the same number of units in this many sets that can be thought of as sets that produce this many units, then the same rules of addition apply and the same rules of ratios apply to the results of that addition. That makes this many units in this many sets that can be thought of as units that produce this many units. In other words, 5 halves plus 5 halves is 10 halves. Since the number of units in each set is a grouping of complete units, this can be understood as the number of units in each set. Therefore, 5 halves plus 5 halves is 10 halves, which is 5. Ratios can be multiplied as well. Simply use the same rules for multiplication that you have already learned for both the number of overall units and sets of units. You do not need the same number of units in each set to multiply ratios. If you have this many units in this many sets that can be thought of as units that produce this many units multiplied by this many units in this many sets that can be thought of as units that produce this many units, then you simply use the same rules for multiplication that you already know to multiply the overall number of units in each ratio, as well as the number of sets that can be thought of as units in each ratio to produce a new ratio. So 5 halves times 5 thirds is 25 sixths, or 4 1/6. To divide one ratio by another ratio, simply switch the quantities of units and the quantities of sets in the ratio that is doing the dividing, and then multiply those two ratios. So this many units and this many sets that can be thought of as units that produce this many units divided by this many units and this many sets that can be thought of as units that produce this many units is just this many units and this many sets that can be thought of as units that produce this many units multiplied by the ratio produced by switching the quantity of overall units and the quantity of sets that can be thought of as units in the ratio that is this many units in this many sets that can be thought of as units that produce this many units. In other words, 5 halves divided by 5 thirds is 5 halves times 3 fifths, which is 15 tenths, which is 3 halves. Sometimes ratios are irrational. For example, the ratio between the diameter of a circle and the circumference of that circle cannot be written as anything other than just the ratio between the diameter of a circle and the circumference of that circle. So we will give that ratio its own little symbol, and we will call it pi. If we divide a unit by 10, then we produce tenths of units. If we divide those tenths by 10, then we produce tenths of tenths, or hundredths. If we divide those hundredths by 10, then we produce tenths of hundredths, or thousandths. Since these divisions by 10 produce numbers that are related to 10, and we have 10 symbols in our digit system, we can create another digit system specifically for ratios or fractions that relate to 10. The first division by 10 is tenths. The second division by 10 is hundredths. The third division by 10 is thousandths, and so on. We will denote this by digits on the other side of what is called a decimal and go in the opposite direction than digits for counting. The symbol for a decimal is the period, unless you live in other countries. Then you use a comma or something. The ratio between any number and 100 is also a special ratio. This is what is called a percentage. Any ratio of any number can be converted to the ratio of some number to 100. That number is the percentage of the first number in the first ratio to the second number in the first ratio. This is often used in finance. A loan has interest that is calculated as a percentage of the loan. An investment has profit that is calculated as a percentage of the investment. You know, that gets me to thinking. Some people say that usury is unethical loans. I don't know where they came up with that. Usury is charging interest on loans, any interest, period. The Christian faith forbids this. That is why Jews are stereotyped as being heavily involved in banking. Because when the banking system was created, only Jews could openly charge interest on loans. You see, people used to take this stuff a lot more seriously back then. Kind of makes you wonder, what exactly is the difference between charging interest on a loan and making profit on an investment? Well, some would say that the loan has a predetermined interest, whereas the investment does not have a predetermined profit. Some would also say that the government will intervene if a loan is not paid back, whereas the government will not intervene if an investment is not profitable.
The basic idea which comes across from reading US strategy papers is the construction of a new grand enclosure. And to put inside this grand enclosure, the United States, 51 other countries, 1.6 billion people, and 2/3 of global GDP. To integrate Latin America away from Brazil and towards the United States, to integrate Southeast Asia away from China and towards the United States, and to integrate Western Europe, pulling it away from Eurasia as a whole and towards the Atlantic.
Of the three big T's, WikiLeaks has revealed 4 chapters of the TPP, which affects 12 countries in the Americas and Southeast Asia. We also obtained and released the core text of TISA, which affects 52 countries, including the EU. But nearly all of TTIP is still secret.
Nobody knows about what's being negotiated in our name. So you have these far-reaching deals which are going to completely change the face of our economies and our societies, and yet even elected parliamentarians know nothing about it.
These agreements are basically corporate ownership agreements. The funny thing about free trade agreements, as we understand them, is they often have nothing to do with trade in the sense of the mutual lowering of tariffs. What they're about is enshrining an investor rights regime in the respective countries and ensuring that corporations can run wild in the respective economies with very, very little regulation or impingement by government or authorities.
These treaties will have huge, huge implications for literally almost every critical issue that an individual citizen or community would care about: health, education, the environment, privacy, and access to medicines. I mean, the list could go on.
One of the most criticised aspects is a system called the Investor State Dispute Settlement, or ISDS. It's a secretive international tribunal that allows companies to sue states over virtually anything that they can claim affects their investment.
If a protest affects their profits, they can sue. If laws affect their profits, they can sue. If new regulations might impact where or what they want to do with their money, they can sue.
This is a new power which will be handed over to US corporations to sue the governments of Europe in a parallel judicial system which is available to them alone. So people have no access to it, domestic firms have no access to it, governments have no access to it. It's just there for foreign investors, in this case, US corporations.
Based on ISDS history, critics argue that European state sovereignty and democracy are at serious risk. Previous lawsuits include Swedish company Vattenfall suing the German state for $3.7 billion for phasing out nuclear energy. British American Tobacco sued Australia for passing a law limiting cigarette advertising. The French company Veolia sued Egypt for raising the minimum wage.
Well, that is weird. So there is someone who intervenes if the investment is not profitable. They are just not labeled with the Latin word for to control or govern. This ISDS is not labeled with the word government, but that is just semantics. It seems that modern day investing is enforced in a way that is quite similar to a loan. Well then, that just leaves uncertainty. Uncertainty is the only real difference between charging interest on a loan and making a profit on modern day investing. What did you have for breakfast this morning? I don't know, but I bet it had more than one single difference from usury. This reminds me of Adderall and crystal meth. Adderall is an amphetamine and crystal meth is a methamphetamine. The one and only one difference between an amphetamine and a methamphetamine is that the amphetamine metabolizes in your system slower than the methamphetamine. Adderall is literally slow-release crystal meth. What did you have for breakfast this morning? I don't know, but I bet there was more than one single difference between that breakfast and crystal meth. What did you have for breakfast this morning? I don't know, but I bet there was more than one single difference between that breakfast and usury. Uncertainty is the only difference between a loan and modern day investing. Modern day investing is uncertain usury. Those who engage in investing clearly are doing so for the same reason as those who engage in charging interest on a loan. Their motivation is usury that they hide behind a veil of uncertainty. Whoever it is that is hiding usury behind a veil of uncertainty had better not consider themselves some holier-than-thou Christian, because if you did, then you would be false. Some people say that the little Vatican is the largest investor in the history of the world. That makes that little church guilty of the largest act of uncertain usury since God said, "Let there be light."